Okay, number 6, we have a situation where a constant torque of 40 Newton meters is applied to a flywheel. We're given the mass moment of inertia of the flywheel, the fact that it starts from rest, and we want to determine how much time it is required to get the flywheel spinning fast enough so that it has 1500 joules of energy stored up. So in reading through this, there's several parts to it. The first part would be to determine how fast does it need to be going to contain 1500 joules of energy. Alright, so we want to find some sort of omega. We know that the kinetic energy of a flywheel rotating is 1/2 I omega squared. Alright, so the question is, for 1500 joules of energy, what's omega? So we're given I of 60 kilogram meters squared, and we want to find omega. Okay, so working through that, I'm going to use solver. Even though this is a fairly simple one, minus 1500 plus 0.5 times 60 x squared. And let's see, a guess of 50 sounds good. But in actuality, it's 7.071. Alright, 7.071. Let's look at units here. A joule is the same as a Newton meter, and a Newton is the same as a kilogram meter per second squared. Okay, so we can cancel some stuff out here. So on this side, let's see, our kilograms will cancel out. It looks like our meters, got 2 meters over here and meters squared over here. So we'll have inverse seconds on this side. So when we take the square root, it's going to be seconds, and our units would be radians per second. Okay, that's the first part of the problem. You have to understand that you can find the rotational speed for a given amount of kinetic energy in a flywheel. Okay, so now we're going to do a constant acceleration equation to find time. Okay, but we don't know an acceleration yet, so let's look at what else we are given. Alright, so we're given a constant, come on, meant to get a highlighter. We're given a constant torque of 40 Newton meters. There's that mass moment of inertia we had before. Starts from rest, and we've already used our 1500 joules. So this constant torque is going to let us relate the torque in I and alpha. So it's accelerating. It's going from rest, spinning up to this speed. So this determines how fast it accelerates, thus how much time it takes. So 14 Newton meters is equal to 60 kilogram meters squared alpha. So alpha looks like that's about 2/3. Again, we'll look at the units here. Newton meter over kilogram meter squared. Okay, and a Newton is kilogram meter per second squared. So again, the units do need to work out. So we get radians per second squared. And there's our 2 meters. So we have our second squared on the bottom. Okay, so alpha is 0.667 radians per second squared. Okay. So we can use the equation omega final is equal to omega initial plus alpha t. Okay, that was 0. So t is equal to omega final over alpha. It's 7.071 radians per second over 0.667 radians per second squared. And that number comes out to be, let's see, that's my x divided by 0.6667, bunch of that, 10.6 seconds. Just to review, the key concept was to use an energy equation to get a final velocity, angular velocity. Use torque equals I alpha to get the corresponding acceleration based on our given torque, and then use a constant acceleration equation to get the time.